joint work with Professor David Ketcheson, who is my advisor at KAUST. Uh, First of all, I would like to thank three people that you all know surely, Professor Masha Berger, Randall Lebeck, and Kyle Manley for the very valuable feedback they have given us during the development of this work. Allow me to start with a bit of an introduction on this type of equations. So we know that under reasonable assumptions, the surface water gravity waves are described by the Euler equations. Ideally, we will use this set of equations to model tsunamis, but the boundary is moving with the flow. So to develop large scale solvers for this set of equations that are also robust and efficient is just not feasible at the moment. That is why we use simpler models. We get simpler models commonly through the shallow water assumption, which is assuming that the characteristic length of the waves is much larger than the characteristic depth of the water. With this assumption, we get a whole zoo of approximations of the Euler equations. In particular, we are interested in three of these models. The Saint-Venant or shallow water equations, Sergey-Nagdy or SGN, and a mile-bottom approximation of SGN. Of course, of these three models, SGN is the most general one. Under certain assumptions, we can recover shallow water equations or its mile-bottom approximation. But why would we want to model these more complicated systems? We have already seen very good motivations to do so in the previous talks. And the key idea is dispersion. If we see the phase velocity of all of these models in the long wave limit, as you can see in the top right plot, all of the models coincide. But as we slowly depart from that long wave limit into higher frequency modes, shallow water equations are no longer such a good approximation of Euler equations. This can be more clearly seen if we take, for instance, a radial hump on the surface elevation here at the corner of the domain, um, and we evolve the system. Here, the depth of the water is very large with respect to the surface elevation, so the behavior of the solution is linear. And you can see that there's a striking a difference between SGN and the shallow water equations. And this is a good moment to tell you what my talk is about, which is about a hyperbolic approximation of SGN. The idea behind this project is to have a GeoClaw implementation of a model that we interpret as being a middle ground between the shallow water equations and SGN in terms of computational cost and resolution of dispersive properties. In this work, we consider two hyperbolic approximations. One which is an approximation of SGN in the top, and one which is a hyperbolic approximation of mile-bottom SGN. The advantage of having this type of models is that being first order, there is hope that we can develop explicit schemes for these equations. And we don't have to worry about, for instance, solving a large coupled linear system of equations at each time step with AMR. The key idea behind these hyperbolic approximations is the hyperbolic relaxation parameter, this parameter c square in the red box. As this parameter c square goes to infinity, at least formally, we recover the original set of equations. You can see this by dividing this by c square and letting it go to infinity. We recover the original set of equations. In the mile-bottom case, you can see that there's this constraint in the original equations that doesn't have any time evolution. In the hyperbolic case, all of the variables are evolving. So we need c squared to go to infinity, but at the same time, the flux Jacobian, the eigenvalues of the flux Jacobian of the hyperbolic system depend on this parameter c squared. So if we want an explicit discretization, the CFL condition is going to force us to take a lot of small time steps. So how large does this relaxation parameter have to be? It turns out that, at least from a linear perspective, it does not have to be that large. Here you can see that if we take a very moderate value of c squared, not close to infinity by any means, we get a very good approximation of the dispersion relation of the Euler equations. Throughout this presentation, I'm going to parameterize this parameter by alpha. Whenever I say alpha is equals to 5, I'm roughly saying that I'm going to, for every step that I will take with the shallow water equations, I'm going to take 5 steps with this hyperbolic system. Okay. Like SGN, these hyperbolic dispersive systems do not have any mechanism to dissipate energy, like turbulence or shocks, like in the shallow water equations. So we need to enforce this artificially. We do it in a similar fashion as Professor Berger mentioned, transitioning to the shallow water equations. These systems allow us to do it in a very natural way. We just turn off the dispersive terms. Here, P is the non-hydrostatic pressure, W is the depth average vertical velocity. So if we turn these terms to zero, we recover shallow water equations. And among other things, we can use the shallow water Riemann solver in GeoClaw, which has survived the test of time. This is not the only way to introduce dissipation of energy. There are these different approaches like artificial viscosity. So how to turn off these terms? We have explored several ways. For instance, a nonlinearity-based triggering. Whenever the steepness of a wave exceeds certain threshold, we switch to shallow water equations to introduce wave breaking. The one that we use most of the time is just transitioning to shallow water equations where the depth of the water is small enough. Again, there are different wave breaking triggering criteria in the literature, very complicated ones, and there is no, to the best of my understanding, general agreement on which one is the best. Regarding the discretization, allow me to just say that we can write the system in this form. It has both of the systems can be written in this form, where we have a hyperbolic part and a source term. The source term doesn't have any differential operators, it's algebraic and local. Uh, so we proceed with operator splitting. For the source term, we have the advantage that it becomes linear in the primitive variables. So we go to primitive variables, solve this ODE at each cell, and then we go back to conservative variables. This exponential of this small matrix works only for simple scenarios like wave tank tests. For real world problems, we use something more robust. We use an L-stable second order implicit integrator. For the hyperbolic part, we use a row type normal Riemann solver based on F waves. And for the transverse Riemann solver, we use the full eigenstructure of the systems that we already have available in explicit form. So how does the solver behaves in 1D? We can start with solitary waves over a flat bottom, for which to compute the initial profile here, we just solve this ODE system to very high accuracy. We use Runge-Kutta further 8 in this case, and we get at the desired rate of convergence. Even though we're using Godunov splitting here, we're getting second order of convergence. We also validate with non-trivial topographies. We were able to compute this quasi-exact steady-state solution for mile bottom HSN, which holds for finite values of the relaxation parameter. And you can see that we're preserving pretty well the steady state, even though the solver is not designed to capture every type of steady state. It is only exactly well balanced for the ocean at rest, which seems to be enough. We also validated HSN. Here we can do something a bit more interesting. We compare with an exact steady-state solution to SGN. Of course, for this, we have to, since the steady-state solution corresponds to the original system, we have to take a very large relaxation parameter. And since I mentioned that we also have additional variables with this system, with these hyperbolic systems, we need to initialize those properly. We use something that we refer to as well-prepared initial data, which means that we define those additional variables here in the green box as the value they will take in the relaxed limit when C squared is already infinity. This is also a good example to show you the effect of the mile bottom assumption. You can see here that mile bottom HSN is not able to capture this steady state, which might not be so surprising. But this is actually an outlier. In most of the tests we have tried, both of these systems perform almost the same, even with very complicated topographies, as you will see in a moment. Now some verification in 1D. This is a dam break problem proposed by Suarez Frazao and Sec, uh, where, of course, instead of the Riemann solution that we will get in the shallow water equations, where we have a rarefaction and a shock, we have a dispersive shock wave that is propagating. We do this for different fruit numbers, and here's the comparison with experimental data. You can see that there is very good agreement with experimental data. Here the green line is hyperbolic SGN, and for reference, I'm plotting SGN also in a magenta line. You can see that the agreement with experimental data is fairly good, and more importantly, I think the match with SGN is also really good. The lines are on top of each other for at least for the leading waves, even though we are taking a very small relaxation parameter. Again, here, for each shallow water step that we will take, we are taking 3 steps of this hyperbolic SGN. Then let me move to Sinolakis wave tank experiment. This is a soliton propagating over a simple slope. We use this test to compare the effect of different transitions to shallow water equations. The light green line indicates, for the light green line, we are transitioning dynamically using the nonlinearity criterion that I mentioned. And for the orange one, we are just transitioning in shallow water. And here you can see that the nonlinearity criterion is very aggressive. Like, it's switching to shallow water when it shouldn't. But for this particular problem, the eventual run-up does not seem to be that sensitive to the wave breaking criterion, which might not be the case for for closer to real world scenarios. Another 1D verification test. This is a large wave flume experiment which tries to mimic the interaction of a soliton with a continental shelf. At the bottom, at the right, you have a box with a zoom-in solution. And we can see that there is some dispersion that we want to resolve for this problem. And here's the solution, different gauges, a comparison with experimental data. Again, the hyperbolic SGN is on top of SGN, and both of them agree pretty well with the soliton fission, except for the bottom right plot, where we can see that we should have introduced some dissipation, some transition to shallow water equations dynamically. Uh, let's move to 2D. We start with a quasi 1D problem. This is just the interaction of two solitons across the diagonal. This is just to validate the AMR implementation. I'm using 5 levels of AMR here with refinement ratio of 2 between levels. And we can see that the resolution is pretty good. At the right, you have a comparison with a 1D solution of SGN across the diagonal. And even though the 2D solution is fairly coarse with respect to SGN, they agree very well. We also compare with a radial hump on a flat topography. For this, we compare with a 1D solution across the main diagonal. Of course, for the 1D solution, we need a forcing source term that accounts for the dimension that we are stripping. And we get, again, good agreement, so we can trust in our 2D implementation. You might have noticed something here at the bottom plot. There is some very fast, small amplitude wave train that is traveling faster than the physical wave train. And we can explain this artificial wave train again through the dispersion relation. These hyperbolic models having more equations than the original equations, that the original sets of equations have artificial phase velocities. So here in orange, you have the phase velocity that will converge to Euler in the relaxation limit. And in violet, you have an artificial phase velocity. As the relaxation parameter increases, this phase velocity grows and grows. So the larger the relaxation parameter, the faster these parasitic modes are pushed out of the domain. The way to get rid of them is just to prepare well our initial data such that no parts of the spectrum correspond to this parasitic phase velocity, which is a non-trivial task. Uh, Now let me move to, to some tests on map grids. A nice advantage of having a first-order system, dispersive system, is that we can easily use map grids, taking into account just taking the metric terms into account as in AMR claw. Actually, this what I'm going to show you is implemented in AMR claw, but for a flat topography, it's close enough to GeoClaw. So let me start with a soliton propagating through a branching channel. The soliton comes through section A and splits into B and C. We consider different angles, and the advantage of having a map grid is that we can have inclusions that are perfectly aligned with the grid lines. We try this one with 90 degrees. This could have done this 90 degrees one could have been done without a map grid, but still. And this is one with 135 degrees. This is the solution at different gauges. The top row is at the main section. It's not so interesting. The bottom row is at the branching channel, and it has some interesting behavior. For instance, we can observe that when the channel is very narrow, the wave that is transmitted through the branching channel, it behaves almost like a soliton, which is almost 1D behavior. And as the channel gets wider, there are more two-dimensional interactions that destroy the structure of this transmitted wave. This has been seen in the literature for weakly nonlinear models, and I'm not sure if this has been done for a fully nonlinear model like we are doing now for SGN. Another verification test in 2D is one of a soliton interacting with an immersed cylinder. Here we use this map grid such that the boundaries of the cylinder are perfectly aligned with the grid again. And we compare the solution at different gauges. We use 3 levels of refinement for this test. And here is the solution at the different gauges with the shallow water equations in blue for comparison. And you can see that HSGN is approximating fairly well the data at the gauges, where the shallow water equations, of course, are breaking and missing at least the initial peak. Now let me move to some verification tests with closer to real-world experiments. These setups have been kindly shared with us by Professors Berger and Lebeck. Let me start first with the Japan 2011 earthquake tsunami. Uh, the color plot above is using the UCSV source, and I'm plotting mile bottom HSN, SN, and the shallow water equations. And you can see that as the solution evolves, mile bottom HSN and SN are both capturing this dispersive behavior close to the transect that the shallow water equations are missing. And in the bottom plot, you have the solution across this transect, and you can see that both hyperbolic models are just on top of SGN. The mismatch is very small, even though the topography here is fairly complex. Here we also have the solutions at the two gauges I'm plotting here. And again, both hyperbolic approximations are on top of SGN. For all of these tests, I have used a fixed relaxation parameter of alpha equals 3. So we are taking, again, 3 steps per shallow water step. And I think it's remarkable that using such a small relaxation parameter that should be infinity, we get such a close approximation to SGN. And allow me to conclude with a hypothetical asteroid impact. Again, we compare mile bottom HSGN, SGN, and the shallow water equations. After the first time frame, we can see some interesting behavior around the initial condition. Again, these parasitic waves leaving the domain. And this is because for the additional non-hydrostatic variables for this problem, we're initializing those as 0. So the initial data for the hyperbolic model here is not well prepared. Despite that, we can see that the hyperbolic model is resolving the dispersive effects pretty well. Matches pretty well the behavior of SGN in contrast with the shallow water equations. Here you can see the solution evolve. And something to mention here is that I'm using a very, very thin sponge layer for the hyperbolic model, which does not like constant extrapolation at boundaries. That's something to have into account. And here you have a close-up near Westport with a transect at the right. And you can see that the hyperbolic models, again, at least for the leading wave, match pretty close as yen. But for this particular example, the trailing waves for the hyperbolic models are close to each other, but not that close to SGN. Still, I will say that both of them are closer to SGN than shallow water equations. But we are investigating the reason for this mismatch because it happens in particular for this example. And so far, we believe it is related to the fact that we are not initializing, we are not preparing well the initial data. It didn't matter much for the other tests because though in those the initial data was hydrostatic, but in this particular case, the initial data is highly dynamic, is moving very fast from the very first frame. Finally, here's a computational cost comparison, a preliminary one. Uh, I'm considering the three different scenarios, a radial solution over a flat topography, the Tohoku tsunami, and the hypothetical asteroid tsunami. And I'm writing down here the relative cost with respect to the shallow water equations. And you can see that mile bottom HSGN is a pretty nice, pretty attractive alternative to other models. This is run on 8 cores on a single node. But you might be wondering something. All of this time, I've been telling you for each shallow water step, with the hyperbolic models, I'm taking 3 steps. So really, I should just be paying 3 times the price. And there are several reasons for this mismatch. The first one is these hyperbolic models have more variables to take into account. So we just writing in this data already implies some cost, without mentioning the Riemann solver and so on. Something that is even more important is the fact that dispersion requires refinement in bigger portions of the domain. So for instance, in this plot, you can see that for the shallow water equations, we could just refine around the leading wave, whereas for the dispersive model, we just need to refine almost everywhere. If we want to capture dispersion. So there's a portion of the computational cost that is just unavoidable. And one remark that I think is very important here is that this is not an efficiency comparison. This is just a computational cost comparison. Since we're taking more time steps than the ones we will take, for instance, with shallow water equations or SGN, numerical diffusion accumulates faster. So with the same refinement, with the same grid, we have a slightly worse resolution with these hyperbolic models than the one we will get for SGN, for instance. So proper efficiency will require a different type of study. As a conclusion, the hyperbolic approximation of dispersive waterway models seem like an interesting alternative, especially with AMR, because we can naturally use AMR with subcycling and whatnot and map grids without worrying too much about these high order terms and mixed derivatives. Something that I didn't mention in this talk is improving the dispersion relation. This is something that we are interested in. We have not seen much work of this regarding hyperbolic dispersive models. And we are using this type of techniques for other systems. For instance, nonlinear Schrodinger in 2 and 3 dimensions, and the results look promising. So with that, I would like to thank you for your attention.